Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. It's been a while since I did one of these. I think it was in March I did the last one. First of all, yes, I'm aware that my green screen's all messed up. It's just the lighting is really hard to predict in the summer and changes all the time, and I just don't want to bother dealing with it, so whatever. Although I am a little surprised it's as dark as it is, but I can move my light around. Anyway, so a little update on what's been happening last few weeks. Well, a lot of things. I think I mentioned on some previous streams that like being in lockdown and stuff kind of got to my head more than I thought, so I haven't been able to stream as much. Or really focus that much on a lot of things, to be honest. And so I thought I was gonna like stream more demo scene stuff on Sundays, and then that didn't really materialize. And I ended up actually kind of dropping a lot of my projects and working on music for the first time in a while. Like really diving into it, which has actually been awesome. Like I feel like I'm making a lot of progress in terms of like my ability to make the kind of music I want to hear, which is really, really cool. It's been, like I said, a long time since I've felt like that. And I think after the EP that I put out in 2014 on Most Addictive Records, after that, I kind of like felt pretty burned out on music, and I never felt like I really got back into it until like the last couple months. So that's been awesome. But as a result of that, I haven't been working on like anything else. And I think that's been fine. Like it's good to get a break every so often. But one of the things that I totally didn't do, which I should have done, was do a stream to catch up on the latest developments on the Xenowing. So at the end of March, I think I did a stream where I was going to start preparing for my compression talk for Vision this year. I almost said but that's not really appropriate considering it was remote. Anyway, that went really well. But yeah, anyway, the stream where I was going to prepare for that, I briefly mentioned that weekend I had gotten a bunch of stuff done on the Xenowing and got it to like a place that was good to put down. So I could focus on some other things for a couple weeks, which totally worked. But I never talked about like details about that, which is like, it's actually really sick what I did. By the way, thank you guys so much for the subs. That's awesome. And by the way, thanks for coming back. A lot of you guys like Daniel Collin and Chief Sector and Dark Second, like haven't seen you guys in a long time. So it's nice that you guys are still into this and hanging out. So that's pretty cool. Did I miss anyone? Mad Moose? Sorry about that. Alkama, Molive. That's awesome, you guys. I like these pride emotes. That's cool. Sorry I didn't send one to you, Dark Second. I didn't see the notification. But I guess I can still do that, right? Good point, Dark Second. Hey, it looks like you did unlock emotes, Alkama. That's great. I still need to make emotes for my channel. Anyway. So I'm extremely proud of like the progress I made on the Xenowing the last weeks I was working on it. It's a bit Rika 9, how's it going? It's a bit fuzzy in my head because it was 10 weeks ago or something now, but I'm gonna like rediscover it live here, which I think will be cool. I remember the main gist of it, so I don't know what I was working on the last stream, but to give you guys a bit of overview and kind of get back into this. So the Xenowing is I'm going to start calling it a demo console. I don't know if I started introducing that term on the last streams, but I've been calling it like a game console, but it's definitely a demo console because that's what I'm going to make on it. And it's definitely inspired by like Dreamcast and PS1 and that kind of era of hardware. I understand that that's two different console generations, but I wanted to capture like that whole range, I guess. 90s 3D video game hardware. And originally it was supposed to be like an earlier accelerated platform. As Talk Dog, how's it going? Hope I said that right. But then I started working on, in order to get some like test content, I started working on this like GL 1.1 front end. So that I could run late 90s and early 2000s hardware accelerated demos that ran against OpenGL. I could run that against like a test renderer that I built in software and test rasterizer. And then the idea was always to take like the core of that rasterizer and then massage it into a form that I know I could turn into hardware. and then make that the rasterizer of the Xenowing, which I think has been a really cool idea. But one of the things that happened there is I got a bit of feature creep. So like now I totally want perspective correction and filter textures and all this other stuff, which is fine. Like I've been enjoying kind of designing how all that's going to work. And I don't know how much of that design that I've really written down or published anywhere. So I don't know if I can really like point you guys, if you aren't familiar with this project, I don't really know if I can point you anywhere that's useful. In fact, even the repo doesn't have a README. Oh, I feel like I actually wrote that or started writing that recently. Maybe I should add that. Anyway, that's pretty cool. And then I still have the rasterizer, which is in like prototype phases, and it's not done. It's not ready to be converted to hardware yet. So one of the things I want to do today, which is actually like I think going to be the primary purpose of this stream, is that I want to start looking into hardware dividers, because that's not something I've ever looked into before. I did a little bit of research beforehand, and I have some notes. So I actually think I already know what kind I'm going to use, but then actually implementing it, I don't know how that's going to look yet. So as anything should be done, I think I'm just going to start with like a software implementation until I can understand the algorithm. And we'll talk about the constraints that kind of needs to satisfy and why I chose the algorithm I'm going to choose anyway. But yeah, back to where I got the Xenowing. So I have this Kaze project. And this is like an HDL embedded in Rust. Wow, you can really see how messed up my green screen is there. Have fun with that, encoder. And this I got actually to a pretty good point, like a good stopping point here. So it's still like 0.1, 0.7, I guess. I guess I bumped the version whenever I like release it, even though. So like it's kind of weird to actually release this project, I think, because it's, and I didn't really make it very clear with this README either, because it is kind of its separate thing. Like what I want from this is to have a little hardware language that's embedded in Rust as an API that I can just make whatever with. And the Xenowing is the driving force behind the features that this project has, but I feel like this needs to be decoupled from Xenowing because of the way that I want to use it. Like eventually I probably want to make a sound chip or something, and I want to be able to do that. Oh yeah, Olive, yeah, that's exactly it. This is the corner of my 4K screen. You get used to it. I mean, the contrast helps. I'll bump this up when we actually start looking at code, but yeah, that's pretty good. Anyway, the reason I'm bringing this up is because this goes hand in hand with a lot of the progress I made. So I was working on Verilog Gen, it looked like, from the name of the last episode, and I totally got it to the point where it generates working Verilog, and I actually got what little bits that I've re-implemented of the Xenowing in Kaze working on the actual hardware. That's like the main gist of it. And I did some really cool things with that. So let me actually try to run this again. I need to look at the make file. That's why I have this pulled up, because I need to see. Yeah, whoops, that's not how you do that in VS Code. This is how you do that in VS Code. Like I was really pumped about it. And you guys can imagine that's why it's such a great like stopping point. So if I just look at this, yeah, there's like make RTL clean. There should be some make tests here. Buster test, compliance test. It's like if I do make test, I'm actually just going to do that really quick. Yeah, we're going to build some stuff, so this might take a minute. Yeah, I switched to VS Code. I'm very happy with that choice. I've been using it at work for a long time, and then only switched at home somewhat recently. So yeah, I'm just waiting for my stream to freeze. But I also want to see that this works still, although I expect it does. Oh no. Is it bad that I actually get some enjoyment by the stream freezing, or from the stream freezing? I just think it's funny. I feel like it's probably fixable if I configure some stuff, but I also think it's fine because it's only when I'm like building, and not every time I build either. Streaming through the Xenowing, that's great. All right, I think we're past the Rust parts. So what's happening now is it's actually running the risc-v compliance suite against my implementation of the Xenowing CPU with a little bit of bootstrapping. I think I showed that before, that I had the CPU running against these compliant tests. I think I showed that before. Because Kazai generates either a Rust sim or Verilog. Now it generates Verilog too. That actually works. Speaking of works is not good. That actually applies here too. Like, this does seem to pass the compliance suite. It does ignore a couple that I don't support, which is fine. And I also should actually really update. I should really update the compliance suite. It seems that there's been some commits there. Yeah, we actually have regression tests both in the Xenowing and in our demo tool as well. But long story short, there's no way I could do this project without tests. There's no way, because it's just too big and too complex. Like, this amount of different modules, I feel like that's not that hard to do to manage in software, but in hardware, at least for me, it's extremely difficult. With everything happening at once in multiple pieces of hardware, that's tough. So I have a bunch of tests that I wrote against the generated Rust code. And this is running through a bunch of them. So there was the CPU, so that's tested, Marv, it's called. And then it tested the low-level FIFO implementation. And then it tested what I call the peak buffer, which is this thing that can pull out of the front of a FIFO and just gives you a slightly nicer interface. So like, if data's, like, it will always sort of pull the last thing out of the FIFO and then have the data ready, so you can get, it's like, it gives you the ability to read out of the FIFO like on the same cycle, but actually has like 1 cycle delay or something. That's just to make it easier. And then it went through it tests that with a bunch of random tests, same with the FIFO and everything. What else did it test here? Yeah, then it tests Buster. And Buster is my my like reusable bus component. Yeah, maybe it's actually worth just fixing my OBS priority. I'm just going to do that. Let me know, by the way, if any of my like explanation of what I just talked about was stuttering and freezing. I'll just say it again if that was the case. Okay, so actually OBS has some settings for this. I see no reason not to do this, so I'm just going to try it anyway. Maybe it helps. Process priority. High. Apply. The audio is good? Yeah, that's fine. Then I don't care. I don't care if only the video is bad, because it was just scrolling text anyway. But yeah, then there's Buster, which is like this reusable bus component that I did some streams on, where you could have like multiple primaries and multiple replicas that you could hook together, and it would just work. And so I have some tests on that. I don't know why this seemed to run twice, but I don't really care. And yeah, there's a bunch of like randomized tests for the FIFO and everything, and Buster stuff. So anyway, this seems to work. And then that's sort of the individual components. And then what I did is I have, let's see, I think it's in Sim. No, it's in MISC now. Yeah, because I have the old Xenowing blaster and I revived that. That's what I did. So if I go to the MISC Xenowing blaster, and this isn't in the make file yet, I think. XW blaster. Cargo run release. I don't think it actually needs to be done in release, but we're gonna do some more building. Maybe the stream doesn't freeze now. I'm gonna move around a lot so I can see. Oh, that sun sucks. But it looks like that might have helped actually. So that's great. Oh, no, there I saw it stream a little bit. Or at least on my end I said stream a little bit. It's streaming a lot of it, but it's froze a little bit, that's the word. Oh well, I'm not gonna do anything more than that. I guess again I could limit the number of jobs, but anyway. Yeah, moving blue noise, that's probably what it looks like. It's bright. Oh, hey, that just worked. Right. Yeah, so this is actually cool. So I just ran this. And let me show you the output here. Oh, I can't do page up on that? Oh, that's fine. I'll just scroll up. You'll see these LEDs update a bunch. So I know this text is going to be a little small, but I'll explain what's happening here. So the Xenowing blaster, this is a program I wrote with the last iteration of the Xenowing that I brought back. So the idea behind this is that this is sort of how you connect from the host system to the Xenowing. And the original purpose of this was to watch for like the last revision of the hardware had a program ROM. And I wanted on the host for it to like watch the file system for changes on the ROM file and then re-upload it to the hardware. However, I decided that way of doing things wasn't that great because I had to have like reload hardware on the hardware, if that made sense. So I decided to change how that works. So I actually have two ROMs now. I have rather a ROM and a program area in memory. So now I have the ROM is actually baked into the hardware, and then there's the program. The ROM, the first thing it does is it requests a file from the host. And eventually I want to change that to have it like read from SD card or something. But right now it just asks over UART. There's a little protocol there. So it asks for the program, and then as it transfers the program back to the Xenowing, then it updates the LEDs as it's doing that. And that's mostly for me to see that it works on the actual board. What you're seeing here is this isn't running on the actual board because Kaze can generate a simulator in Rust or Verilog. Since I just ran Xenowing Blaster with no arguments, it actually sets up the simulator. So yeah, it says creating sim device, and then you can see Xenowing Blaster engage, all systems are go. Ev.029 actually comes from the ROM. So that's outputting over UART, and then it requests a file, and then we send it the file, and that's what all this is. And at the end, you can see the ROM then outputs program RAM read successful, and then it jumps into the program RAM that it just read from the host. So now it says hello from program RAM, get ready for some fade babe, and it will do some random tests, whatever. So that's pretty cool. And the other thing is if I do this, and I think I add, for example, comp5, which I think is where the actual hardware is. Now it says create serial device. So it's actually going to talk to the real thing. So now if I hit the reset button on the actual board, I have to remember where it is. Here, it's this one. Oh, invalid UART command received. I think I got to do this in a particular order. There we go. So now the actual hardware requested this, and then the LEDs blink. I actually don't know if, yeah, and then we get some random stuff. Do that again. And so the idea now is that this will just reload this whenever I like reset stuff. Then it will just request a new program once I reset the hardware. So this is actually running on the actual board, and you can see the output is the same. And the advantage here is that then I can iterate without actually putting things on the board. And then I should get exactly the same thing. So like the host code in this Xenoing Blaster thing, if I go into main, yeah, there's these different devices, sim device and serial device. And then at the end, I have this. You make a device, and then you can do it. Then all the protocol and stuff is implemented here, which I need to clean up at some point, but this is fine. So it's going to try to read a byte from the device, and it might get a putc command just to put a character, or it might get a file read command, and then it'll output the file. So anyway, it's really cool that I got all this working. So obviously there's a lot of stuff going on here. When I build and it generates the RTL and everything, that makes this generated.v file, which is 5,000 lines of generated Verilog for the Xenoing now, which is a lot, but I didn't write a single line of it, which is pretty sick. And there is of course some bootstrapping stuff. So in this, let's see, I think actually in this sim project, this, yeah, Buster, FIFO, Marv, Peak Buffer. Okay, so those are the individual ones. Is it here actually? Yeah, there's build in the Xenoing Blaster. Okay, yeah, this is where I do it. So in the build script for the Xenoing Blaster, you can see we generate code for the Xenoing, and then I add like the LEDs and hook those up, and then I have this UART TX and RX. So I actually make a another UART receiver and transmitter that I hook up sort of backwards to the receiver and transmitter from the Xenoing itself, and that way I get this like byte-oriented interface that I communicate with the sim code, and then it will encode and then decode the UART stuff by reusing these UART TX and RX that the system then uses. So the Xenoing just has like TX and RX lines, and then I hook up an encoder and a receiver or transmitter receiver. The same ones that are used inside the Xenoing, but I flip them around and then I get the byte interface on the other side. So it's a bit silly, but it keeps the Xenoing itself very simple. Also, I don't have the DDR memory stuff hooked up yet still. And I'm not going to do that for a while because it doesn't sound very fun. So we need to do it eventually to have a large enough frame buffer to be useful, but I don't need to do that yet. So I'm not gonna. But yeah, so that's where that's done. And then since that's in the build script, then this sim device thing can create top. And top, I think, is the module. Yeah, I make a new module here called top, which has an instance of Xenoing and then all the other stuff to hook it up. And then that exposes these top level signals. So then here, this is the simulation loop right here. This is the whole thing. This first cycle, I reset the top. Otherwise, I tick the clock and then just check the ports. It's that easy. It's actually pretty cool. And then for the serial device, it's basically the same, except here looks like I'm yeah, I don't know what this, yeah, this is reading, if we read bytes from the serial port, then we need to do something with them, I guess. Yeah, because the read byte is handled from somewhere else, same with write bytes. So this is literally just exposing that serial port, whereas the sim has to run in a simulation loop on another thread. And then I think it uses a couple channels to send stuff back and forth, which just makes it easy. But ultimately, it's also just, it only really has those two, like the UART send and receive. That's really the only way you talk to the device. But then also will, for example, keep track of the last LED's value just to update it in the terminal. Because on the physical hardware, I can see it. But then in the simulator, I obviously can't. So that's what that is. So that's really sick. So just from running this one project, and depending on which arguments I specify, it does the same thing, which is awesome. And of course, that took a lot of work. I had to like overhaul the Xenoing or the Kaze Verilog compiler because I made a bunch of mistakes. So I really went hard on that one weekend. And I found a couple bugs in the hardware as well, in my description of the hardware. And I think I have this in Git. Yeah, so here you can see introduce helpers reg next with default and use for bus control signals. So when you're doing FPGA stuff, or hardware in general, you often will do you'll have some kind of path, some kind of like data path and a control path. So if you imagine like a pipeline for example, a CPU, but it could be like anything. Like I think the bug that this was for was in control signals for the buses. You'll have the data path, which is like where, like, let's say you have a bus and you have some pins. I'm going to call them pins, but lines or wires, whatever. You have some pins that are going to be for carrying data around the bus, and then you have some control pins. So you usually call that the data path and the control path. And one of the things that you need to be careful of is because these data paths can get really wide. In this case, the buses in Xenowing can be up to 128 bits or something. In fact, that's actually the max that Kaze supports to make the simulator simpler, which is fine. Anyway, you typically don't want to have a lot of like conditional logic on your data path if you don't need it. Whereas your control path is usually a lot fewer signals, and so then you can have more complex logic there. And that's kind of the idea. You have all the complex logic in the control path, and then your data path is pretty clean. And you do that mostly to be able to keep your design fast, because the more stuff you have there, like the harder time, like place and route and everything has to actually do a good job. So like a common optimization is to do things like, if you have some registers in your data path, don't give them default values, because then you don't have to have extra hardware to support the reset that will actually change the value in those registers. And of course, this could lead to like logical errors, but you will typically handle that in your control path anyway. So like a lot of the times the value that comes from that data path is going to be ignored. Like this is really common. And in Kaze, I decided, yeah, I want to support that. So I have registers where you don't necessarily have a default value. And the problem is, if you do that in the wrong place, then if a reset happens, you might get a bad control signal from before the reset that is then asserted when the system starts up. So your reset state might not be what you expect. And the problem with that is that unless you, for example, randomize all the register values in the simulator code, your simulator might not actually match the hardware in those cases. And that's actually what happened. So I had some control signals in my buses that weren't being reset on reset. Which I mentioned, this is an optimization for the data path, but you could actually apply this optimization everywhere. So yeah, it looks like several registers in the bus control paths didn't have default values. And I think what I did is actually change those so that they would have default values. So basically what happened is on the device, it just wouldn't work. And I had to actually debug it on there. And it took me a long time to figure out, but it was actually not a Verilog generation error, which is what I thought it was, which is also why it was hard to track down, because that's the part I was working on when I was doing this. But it turns out it was just a logical error on my part that I had some registers in the control path that didn't have reset values. So when I actually started the system up, it was in a state I didn't expect. And again, if you randomize all of the register values in the simulator, that can catch those kind of issues, but it doesn't always. And I haven't added support for anything like that in Kaze, so I might do that in the future. But anyway, so I did have to change the logic for that reason, to actually fix logical errors. But other than that, it mostly just worked, which was pretty sick. So unless I make errors like that, the sim matches the actual hardware, which is kind of the point. And I'm pretty happy with that. So yeah, that's kind of the main bit of progress, is that I've now bootstrapped that. And then again, on the software side in the Xenowing, I have actually two ROMs now, or I should say two programs. There's a ROM and then a program. So I've separated those, whereas before it was just the ROM, but now it's boot ROM and program. And I ended up copying a lot of files here instead of like trying to reuse some of the make files. And that's just laziness. Like I don't want to sit here and figure out what the commonality is yet until I'm a little more sure of that. So I've duplicated some of the Xenowing stuff and some register definitions, and I don't really care about that yet. I might actually try to generate some of those files, which would probably make a lot more sense anyway. Generate the documentation and the header files from some common source. But we'll see. That might just be overkill. It's not that bad yet. So yeah, the boot ROM, obviously there's some like startup stuff. But then it's here, it does a write command to request a file name, and it actually gives the name of the file too. I tested this with different things just for fun. And then it loads that. into the program RAM area, and then eventually jumps to it when all that's done. And then the program itself just has some random test code in it. Hello, and then does some stuff. So yeah, I think that's actually all I needed to catch up with. There's parts of this RTL that I'm not super happy with how it looks. Like this Buster stuff got kind of messy, but it's all tested, so that's pretty cool. There's tester there, and then there's the sim tests as well for that, which we ran earlier. Sim Buster lib is where all the tests are. And I did end up also, there was also another change I had to make actually, which was in Kaze. I decided to change the semantics of the memories. So I had issues where I actually generated some Verilog that I thought was unambiguous, but it turns out I was able to, by changing the size of the memory, I was able to get the Xilinx compiler to generate, it would have to generate different ways to build that memory on the FPGA. So like if I only had a few elements, it would just make registers for that, which fine. That's like the most efficient way you can do that for small memories. And then a little bit larger, it would generate a certain kind of memory cell, and then like a lot larger, it would generate an actual block RAM. And I think it was registers, and then distributed RAM, which I think is also registers, and then block RAM. And so at different sizes, I could see that it would generate different pieces of hardware for like the same Verilog. So the same behavioral code was generating different physical things, which again is fine as long as they all behave the same, but they don't. And as it turns out, if you're trying to get this Verilog compiler to infer which kind of RAM you're using, you need to be very explicit about that RAM's behavior, and certain behaviors aren't necessarily supported by every Verilog compiler. I chose to take a pragmatic approach about it and just make, again, try to find like a least common denominator thing, which works with a compiler I'm testing it with, but it may not work for other ones. And again, because Kaze is not like a really serious project, like I'm not pushing other people to use my HDL. I don't really care, but I do want to share it, so it's available. But those are the kind of decisions I feel like I have the freedom to make, because I'm only really supporting my own projects here. Anyway, I was able to find a behavior that works, but it means that if you like do a simultaneous write and read via two different ports, so if you have a write port and a read port on a memory, and if you write and read to the same location, the value that the read returns originally was going to be the value that was written on that same cycle, but now it's actually, you get the value that used to be in the memory on that cycle. And then if you read that same value on the next cycle, then you would get the newly written value, but you have that sort of 1 cycle delay through the memory. And that was able to be supported by the Verilog compiler. And I think that's a behavior that I think generally is pretty easy for FPGAs and whatever to support. So I did have to make that semantic change, which meant I did have to retime some of the things in the design, but it really wasn't that bad at all, actually. And mostly that was covered by the simulation tests that I did. So I just kind of had to go through that by hand. And ultimately, I think the retiming of the design took like a couple hours, which is actually sick. So yeah, like there's a lot of building blocks here now, and it's getting really exciting. And I've been talking for a half an hour now. So that's cool. I guess I can just jump into what I wanted to get into then today. I mean, I feel caught up enough. Great. If you guys have any questions about this before I switch mental gears, hit me. Otherwise, I'm going to start pulling up the rasterizer. But actually, I don't really need to run the rasterizer stuff now. Because actually I do want to pull up the code, which I don't think I've touched since like November. This project has taken so long. I don't think it's actually taken a long time for what it is, especially considering the time I actually work on it. But definitely took longer than I expected, and that's on me. For a bad estimate, not for being slow, I think. So what I just pulled up is Gloat, which again is public right now, I think. I'm doing all this in the public. I just don't think I have licenses for any of these things, but that's again just me being lazy and not deciding on those. Anyway, there's a lot of things in this project. Most of it's this like really shitty OpenGL implementation, which is only good enough to run the demos that I was testing, and that's all I care about. And then it kind of bootstraps, like it has, I've isolated the actual rasterizer, which is a rasterizer just for one tile. And the idea is that I want to have a rust struct that essentially operates almost identically to what I will eventually have coming out of the Kaze simulator generator, which I don't have yet because I need to massage this before I even start writing any of that RTL. But yeah, that's kind of the idea, and I can sort of get everything to like fixed point, for example, was probably the biggest goal. And also, like, I need to figure out how to handle one of these divides for the perspective correction, because you need to do a per pixel 1 over the interpolated W. So you take W and then you invert it, and then you interpolate that across the face of the triangle, and then you need to take 1 divided by that inverse, which will give you W again. And then you need to multiply that by a couple factors to actually get the texture coordinates. This is like classic perspective correction stuff, and I'm not going to go into that math because, frankly, I don't understand it. Homogeneous coordinates have always evaded me. I asked the Twitterverse about that a while ago and got an awesome thread full of answers, and unfortunately, like, never dug into any of that, which I really need to do. So thank you guys for those who answered. I would love to understand that better. I don't, but it doesn't really matter in this case or in this context, because you really just need to know the math. You do need to have a bit of an understanding about like what the ranges of these values are going to be, so that you can choose like a appropriate number of bits for all the cases that you practically care about, to make sure you don't overflow and stuff. But like in this case, I think all of these are 32 bits by the time I'm interpolating them. I think so. W inverse min is an I32. Yeah. I don't actually know if that needs to be signed. These are the kind of details I need to figure out in software before I ever touch RTL. Isn't homogeneous coordinates just making it so you can do translations with linear algebra? I think it's more about the fact that it allows you to do the projective stuff in a way that's easier. So in this case, the important thing is that we need to interpolate across like in screen space, which is like pixels, but because we've perspective, like we've taken something in 3D and then projected it onto a 2D plane. As we go like step in pixels, a value like in screen space might actually cover like a large depth, if that depth was kind of projected, like if there was a really long line segment and it was kind of at this angle towards the camera, then that would only be a few pixels, but it might have to cover like a large area. So like the mapping doesn't quite work. And if you do it in homogeneous coordinates, which is what I'm doing with this W coordinate, then 1 over W is actually linear in screen space. Again, I don't really understand this stuff, but it has to do with the fact that the math works out better when you have perspective stuff. I really wish I could explain that better. But I think that's kind of the key, is that when you have the projective stuff, more of the math works out. Again, I'm embarrassed that I don't know that better, but such is life. So you do need at least a 4x3 matrix to do translation, or describe it with a matrix at least. So that then you at least need 4 components. I don't know if they need to be homogeneous though to do it that way. I know it works out really nicely. So I'm not saying that's wrong, because I don't really know. I'm just trying to be pedantic about the parts of that I can confirm are right, which is very little. Yeah, I think a lot of us lowly programmers have trouble with this stuff, even if you work with 3D graphics in games for years. but that's something to improve on anyway. But again, in this context, all we really care about is that we do have this quantity, which is in this case 32 bits, that we need to interpolate across the triangle. And after we interpolate it, we need to take 1 over that quantity, which means we have to do a fixed point divide. And we need to do one of these per pixel. And I don't have a very clear description of how this pixel pipeline is going to work. Yeah, sign flipping hell. That is something very... I want to say it's unique to graphics programming. It probably isn't. But boy, do you have a lot of that there. Hi, 286 Tech. Yes, indeed, with a 4x4 matrix, then you can describe the translation in a column, and it all happens in one matrix multiply, which is great. But yeah. Is that the homogeneous coordinates, though? Just the fact that you have another component? Because isn't it more about what it means than the fact it's projective? I'm not really sure. Like, that's the kind of the stuff where I get lost. I understand that, like, these components are the rotation ones, and this is where you do the scaling, and then here's where you do the thing, and I can, like, write out the math and see that that's how it works when I do a matrix vector multiply. But like, conceptually what's going on and how the perspective works, that's the part I have trouble with. Anyway, again, here we only need to do this divide. And I think here, right now I have this described as a 64-bit signed divide. I really don't think that this is going to be the case. I don't think we need nearly that many bits of precision. But that's what I have right now, just because I don't know better yet. But ultimately, the way that this rasterizer works, it's actually really simple. It's based on this old Pineda paper from like 88 or something. The idea is that you set up all these interpolator, like every quantity you need to interpolate. You have a min, which is like where it starts in this tile. Or actually, yeah, I think in the whole tile, because again, it's a tile renderer. So for the tile, the min is the value of this quantity at the top left corner, which may not be on part of your triangle, so you need to calculate it there. And then you have dx and dy. And 3 of those quantities are these what are called edge functions, which represent essentially where you are in relation to a given edge. And so if you have all 3 of those, you can determine if you're inside the triangle or not. And so we go through every pixel and evaluate. We check these edge functions, and then if we're inside, then we actually like shade the pixel. And the way I'm going to do this in hardware is I'm going to design everything as a pipeline. Yeah, Daniel Collin. I do plan on still doing a tile-based renderer. That was probably already answered by what I was already saying, but I only saw your question now. But yeah, so I want to describe the whole thing as a pipeline, which maybe I'll have more pipelines, but I'm thinking just have one pixel pipeline. So for that pixel, you need to again do these edge function checks, and you need to take these other quantities. Again, like you need to calculate S and T after doing this 1 over W divide and everything. Look up the texture coordinates, potentially do blending, like all that stuff. And it's really, yes, thanks to 86 Tech for sharing those, sharing Rig's posts about that, because they're really good. And a lot of that is definitely what I'm using here. Because he also links the same papers and talks about how to do that. Also, I need to reread his sections on top left fill rules, because I don't have that working correctly in this rasterizer, although everything else is pretty good. It takes a lot of like tweaking to get like all the right biases and everything, but that's one part that I've been really lazy. Anyway, it's really good stuff. So you can see like there isn't much code here. For like, this is the rasterizer. There isn't much logic, and that's kind of the point. Like, I'm trying to keep this relatively simple. Now, some of this is cheating already, because like I'm still doing the color math with some 4 component vectors, I think. And that's just because I haven't converted that over to fixed point yet, but all that's going to happen. So like the whole point is that I want to get this all into fixed point math, and I want to have like, there's some multiplies here. and a bunch of shifts and all that kind of stuff. And I just kind of want to unroll like all of this in software before I ever start writing it in the HDL. I'll probably refactor it before I do that too, like into different parts of this pipeline. But yeah, if it's all very basic fixed point math, which is kind of the point, and I can do it all in a pipeline, then the idea is that we just put each pixel position into that pipeline along with these values. And with this kind of Pineda style thing and having this like dx dy, it becomes really easy to feed in all of the parameters for the pixel pipeline just by essentially adding dx to the min value and dy to the min value. So you kind of keep this running like current value. And the first thing you do on like the beginning of a line in your tile is just store it. And then you'll take that value and you'll just add. And then for the next line, you add dy to the thing you stored, and then you store it again and move on. So like I don't know if I'm describing that very well, but it becomes really simple. So the actual rasterizer really isn't doing very complicated stuff. In order to make all this work though, yeah, I also have to do like depth testing. So I'm going to do I want a pipeline that doesn't have any stalls. That's just going to do one piece of logic, and then things like depth testing and blending are just going to be choosing different parameters. So like the way I'm going to describe blending is you don't disable blending, but you have a white texture that has a 1x1 pixel size, or probably 2x2. That's all white. And then you do multiplicative blending with that, right? So you just configure the pipeline to take, or maybe that's how I was going to do flat shading. My point is like, I'm going to have the same pipeline that's fixed, and there's no stalls or anything in it. And you just configure the pipeline differently for all these other different things. So yes, that answers your question, Daniel Cullen. I will not have different rasterizers. I'm going to have a fixed pipeline, and then you configure the pipeline differently, so it will support all those different things. By again, for example, flat shading, or not necessarily flat shading, but like not having a texture, you will actually have a texture. It'll just be a very small white texture. And depth testing will just like, it will always write the pixel, but whether or not it uses just whatever color was already there or the new calculated color is going to be decided at the end of the pipe. And again, this makes the whole thing very, very predictable. And that is actually really important, because for things like a divide, division is one of those things where if you do it like the way you learn in school on paper, or if you do it sort of the most basic ways you can do it in binary, which is essentially the same algorithm. Yes, exactly. Don't call it. It'll be the same speed, the same latency, definitely. Which again, better for worse. Like I guess I could have potential speed wins if I have different rasterizers, but I'm not gonna do that to keep the hardware simple. But yeah, for that kind of division algorithm, as you probably learned from school, the amount of steps you have to take to do the division is actually dependent on the values, which means you have like a non-deterministic latency through that pipe. And that's an undesirable quality for this approach. I would like a pipeline where it always takes the same amount of cycles. And then I can sort of like time the whole pipeline, or again, rather just have a fixed pipeline, and maybe I can even parallelize some of this stuff. I don't know how much I'll actually be able to do for that, though, because this W coordinate is used in a lot of things. So the data dependencies might not allow me to do most of this stuff, but yeah. Anyway, so we need a division implementation that's fixed point, and that takes the same number of cycles every time we use it. Now, the other thing that's important with this is we don't actually care about accuracy too much here. Again, I use like 64 bits here, but that's just because I haven't reduced it. I don't think that like this value is actually pretty, like of all the interpolants, I think is the word there, all the things that we interpolate. I think this is actually one of the more critical ones, but at the same time, I don't think it needs to be that accurate, like not to be 64 bits at least, for sure. In fact, I think the only reason I did that is because we're dividing this 32-bit value. Yeah, you know what? I'm not entirely sure. But I imagine this can be like 33 bits or something. I think that's the point. because it's 1 over this W, and I don't think you need many bits for that. Yeah, in fact, this 1 over fits in 32 bits. And inverse fract bits. Yeah, that's actually 30 even. So I'm actually not sure why I did this as 64-bit. Oh, yeah, this is the number of fractional bits. So I don't remember how many bits I decided are on top of that. I guess 1. Or is that just the sign bit and everything is assumed to be less than, like the decimal point is? It's just a sign bit and then this. Probably makes sense for W inverse. I don't remember, to be honest. And then W frac bits is after we've done that. Yeah, anyway. 24 bits, I can probably get away with that. I think I decided these because, again, those demos that I was running looked really weird if I used different values, but I might have also been feeding them wrong into this part of the pipeline. So I think this needs more tweaking and stuff. But yeah. Yeah, it was definitely the smarter me that understood this. I mean, maybe. It's at least the me with his head in this space. I don't know how smart he was, but definitely smarter than me now, I guess. Anyway, I should get to the meat of this. Because let's just jump straight to the solution here, because I at least took some notes for what I think is going to be what I'm using. Which seems to be, I think it's called Goldschmidt. Oh man, speaking of streaming, I watched it's a music producer that produces Dua Lipa. I think his name's Ian something. Great producer. And he did a couple streams, and so many people commented on how he was so scatterbrained during the stream. And I was just really happy to see that. No, not Ian Ford. Ian Kirkpatrick or something like that. Anyway, I was just so happy to see that other people in other professions are the same way. But I guess I should have predicted that from my experience with pair programming anyway. Especially over Zoom. It's basically the same thing. Anyway. Just to jump in here, I went to the Wikipedia page on division algorithm. Because I did some research. Like I looked at some papers just to see like what kind of methods were being used around different things. And it seems that this non-restoring thing is helpful. And we get to this Goldschmidt division, and there's another, it's also called something else. Yeah, Anderson, Earl, Goldschmidt, Powers, AEGP. And if you search that, like fixed point division AEGP, you actually find a lot of information about that, especially in like VHDL and Verilog. So, oh, totally Drew too. I have exactly the same thing. Sometimes it's really helpful to describe things, but which I'm sure you've experienced as well. But a lot of times it's just you see it right when you're done. It's so annoying. I gotta shave my mustache. It's like poking my nose. Unrelated. Anyway. So I haven't fully wrapped my head around this. I understand this part. So the idea is that this is a division algorithm. This, like Newton-Raphson and some other techniques. The idea is to actually you see you there, Data Colin. Thanks for hanging out. You estimate a potential solution. So you have the divisor and the dividend, and then you want to get the quotient. And the idea is that you estimate a quotient and then multiply the numerator and the denominator by that quotient. And you do that over and over again. So it's an iterative method. And eventually, your goal is to get the denominator to be 1. So you try and pick these predictor values. Yep, it's called, which this calls multiplication factor. I should bump up the size here. There you go. So you're trying to generate an estimate for this multiplication factor, again, such that d is approaching 1. And so then you multiply both of these by that factor. And eventually, if d is 1, then n will be the exact quotient, because then quotient is this number divided by 1, which that cancels. So then you have the quotient, whatever your numerator was. After you multiply it by this factor much times, then you get roughly what the quotient is. And I think some people have done a lot of good work on like estimating how effective this is and how accurate it is. And I'm going to basically ignore most of that. And my plan is to find some existing implementations of this. Well, I'll probably sit here and play around with this in Rust a bit, just like a really naive way to do this, just to like see that it works and kind of get a feel for it. But ultimately, I think I'm going to find some existing like VHDL or Verilog code. Because I think I found some examples of that for like 8-bit division. And as far as I'm concerned, if I can get an 8-bit divider working, then I can get an n-bit divider working. So that should be good enough. And I expect something like this with a relatively few number of steps would be pretty basic. And then as far as I understand, to get this pipelined, you would just unroll the steps. So if you had, 3 steps of doing this, like calculate an estimate and then multiply both sides, then you could do that as 3 pipeline stages. Did I say 3 steps? Yeah, like n steps becomes n pipeline stages. And each one does the same thing where it calculates again this multiplication factor and then multiplies both sides. And at the end of the pipe, you should have accurate enough quotients coming out, which is the dream. And that's about the level of my understanding. And I need to sit here and play with this kind of on its own to feel better about it. But again, because it's pipelined, what you can do is then, if you have 3 stages, it's always going to have 3 cycles of latency. But then also, if you pump in 3 values, 1 every cycle, then at peak efficiency, or like when the pipe is saturated, then you are still producing 3 quotients every cycle as well. Again, when the pipe is saturated. So like this is kind of the right algorithm. And you can see here, Goldsmith method is used in AMD Athlon CPUs and later models. It's also known as AEGP, which for me seemed to give more results. I actually found a DSP book today on the internet. I'm searching this. I don't know if it's supposed to be there, so I'm not going to show it on the stream. But I've saved it for later. I'm going to assume it's supposed to be there. And that, again, had a VHDL implementation of this. In fact, I'm going to see if I can find one, AGP fixed point division. Because I also want to get an idea of like how many steps is enough. And I kind of want to massage all of this until I get a divider. Again, this is why I have the software implementation. I kind of want to massage I want to implement it on its own first, and then I want to plug it into this rasterizer, and then kind of massage how many fractional bits and how many steps the division will need within this framework. Because again, the idea here is that like this doesn't look like a pipeline because it's not implemented that way. This is just Rust code. But the idea is that if I can get it kind of mathematically sound, then I can actually rework it to be a pipeline, and then move that over to RTL. In fact, I may not even do that, convert this to a pipeline in Rust step until I actually write the RTL. But I think I'm going to write it all as these like individual terms, and then I'm probably going to separate this in the software to say like, okay, this is one stage, this is one stage, this is one stage of whatever that pipeline is. And I expect that once I actually do it in hardware, I might have to rebalance. Like I'll probably, I don't know what that's called. I'll probably have too much logic in one stage, and then probably have to move stuff around. So I expect that there will be a lot of iterations for this, which is fine. I don't mind that at all. But But again, that's me talking a few steps in the future. The first thing I need to do is actually kind of code this. So I think the very first thing I'm going to do is just look at this Wikipedia article and not even look at like an existing implementation, but just write my own just from this, just to make sure I understand it. And the reason I'm spending so much time on Division is because I don't know anything about it. So we just got to figure that out. So, and I expect things like, for example, multiplication. My hope is to actually have all these multiplies here. We'll see if these ones can actually fit, but I hope that we can just do multiplies in Verilog and have the compiler give us what we want out of that. And I'm hoping that we'll have few enough of these, and with few enough bits, especially for this color stuff, we can do it with reduced precision, such that they'll all be able to be done in parallel and won't totally balloon the design. So I hope it works. Exactly 2 curves. Yeah, poor Geyser too. And especially poor them if I just assume the wrong gender. Gotta get better at that. Anyway, let's see. Cargo, new, bin. Yeah. Div shiz. So I don't expect to get very far today with this stuff, especially because it's getting hotter and hotter in this room, and will continue to do so. But I just thought I'd share where the project was at, what I'm thinking, and just see how far we get. True, doer too. Very true. Good points. But yeah, a big kind of staple of the Xenoing project as a whole, and I think is embodied by the design approach that I've kind of landed on, which I kind of figured out in November, and I've just been working towards since, is to have all these individual pieces of hardware, like, for example, this rasterizer, just try and keep it as simple as possible. Like, design it with all the features I want. It still makes sense to hardware accelerate this. But then the fact that I'm making it tiled, again, allows me to simplify this a lot. The fact that I'm designing this all as like a fixed stage, like fixed pipeline, means that I won't have to do any stall logic in any parts of it. Like, all meant to be very simple. And then it moves some of that complexity into the software, which I think is appropriate. So I'm going to have some kind of engine that will work for a tiled renderer. But the other thing is too, since I have like all the sim setup, I can run the whole thing in the simulator without even touching the actual hardware. That's going to come in handy because I can do most of the work there, and I can write. Also, the fact that I set up all this stuff so that the actual hardware or my host computer can communicate with the device. I can like generate protocols to do things like register writes from the host computer. So I can kind of test the whole pipeline in sim, and then it should just work on the actual hardware. And so I could like bootstrap just this tile renderer from Rust code essentially, and actually have it power this OpenGL implementation at one point, which I think I'm going to do. So then I know that works before I ever actually have the full pipeline on the actual system running. So I think this is pretty cool. For how many lines of code have you wrote in your life? No idea. Yeah, that's a crazy question. I don't even remember the last time I counted the lines of code in a project. I remember I had a demo engine in high school that reached 20,000 lines, and I thought that was nuts. And that was a long time ago, and I've written a lot bigger stuff and a lot smaller stuff. Generate lines of code is more fun. Again, even this one file from the Xenoing right now is 5K lines or something. And that's fast. I mean, I have an SSD and stuff, and the compilation for this isn't actually very, very expensive. 11,000 lines for one CPP file. That's crazy. And I bet it was like 2 orders of magnitude larger after template expansion. Uh-oh. Rust analyzer ate shit. Who cares? So I just want to come up with like some really basic case here. Right? And so here we should get 4 if we do this. So let's do this even. She'll do it this way. No, I'll do it at the top because this is the function that we care about, is the div function. Make the U8s even, which might make it more tractable. I don't know. It's going to return a U8. So we could do A, for example, which is stupid. On that. Fine, and of course, I should actually implement it because that's easy. Yeah, and there it works. Oh man, that's insane, 286 tech. Yeah, I don't know if you caught that, Molly, but there was a couple days ago where Arcolect, that like generative Twitter curator image thing, actually posted a screenshot of some 65816 dump. That was pretty funny. Yeah, for C64 stuff, I usually have one assembler file per effect, but then you end up with a bit more when you actually start stringing them all together. And the SNES stuff I did had a lot more than that, I think, for different parts. Like I had one assembler file for system setup and one for like interrupt handlers, like for different things. I would kind of slice it up that way. But none of that stuff got very big in the first place. In fact, I think actually for the C64 stuff, I not only had assembler files per effect, but I also had like prototype files, so bootstrap the whole thing so I could run each individually. But for the SNES tooling I worked on again more recently, it's very different. And I won't say too much more about that. But it's extensions of the ideas I've shared on stream before. Just more powerful. Let's see. Yeah, I wanted to implement this actual algorithm. So actually, the first thing I want to do here is change these to doubles, just to make it like really obvious. Because I want to do this like stepwise. And just see that this works as an algorithm, which of course it will, but you know. Yeah, so it's generate an estimate for the multiplication factor. We multiply, and if it's sufficiently close to 1, we're going to be done. But I'm actually going to have a fixed number of steps because that's what we're going to target eventually. So I don't. This sufficiently close to 1 means, or the way I'm factoring sufficiently close to 1 is after n steps. Then we're going to assume that it is, which is still fits. And then here we have something interesting. So assuming n over d has been scaled such that 0 is less than d is less than 1. And that's not necessarily the case here. But I think instead of like trying to figure out what this is in general, I think I'm actually just going to pick numbers that have this condition met. Because that's going to make my life easier. And especially with like this kind of math. So here I picked like 20 and 5. But if we scaled this, right, so that, let's say we scaled this by 10, or divide it by 10, we'd have 2 divided by 0.5. And then the denominator would be in that range. And I think it's basically going to be the same here. Like we can scale W such that it's all fractional bits. And we're going to be able to do the same idea. So yeah, so I'm just going to do this by hand here so that we see that this works. But yeah. So then we do this. We do for in say like this. Number of steps. So we're going to do this. Let mute result is A, the numerator. And eventually you're going to return the results. And actually, let's call this numerator. We can call this n even to match the Wikipedia page. We can do let d is b. In fact, we can also do this way. N and d here, and then just make this mutable. There. Do that. Then we'll say f. So let f is... Yeah, I've been getting into that too. Like use Google Sheets as well. That's a good point that you can see the intermediate stuff. I also like, especially if you're going to graph stuff like this, I think that's really useful. Just do it there. I don't know why I didn't do that this time. But whatever. I agree. That's a good way to do it. So yeah, so in this case, again, we're going to assume this condition, which is fine for this little test. So that's just 2 minus the denominator. Easy. And then we multiply them out. Okay. Equals n times f, and then d is d times f. So this needs to be mutable as well. So this is kind of interesting, right? So after 2 steps, it got to 3.75. I wonder what it got to 1 step. I should probably just print these out at different steps. So yeah, after 1 step, it's 3. Which I guess makes sense. Because f would have been 1.5. And if you multiply 2 by 1.5, you get 3. I mean, this seems to work, right? 5 steps, we probably have something pretty good. Yeah, that gets very close. Okay, it works. Right. So some key things here. Each of these pipeline stages needs to have 2 multipliers and a subtraction. Right? Because if I'm going to do this as essentially unrolled steps, then I need to do this many multiplies and a subtraction for every stage. If I do this, we should also get 0.5 eventually. Just test some basic values. Or 5, yeah, that's what we'll get. I mean, this totally works. That's kind of cool. I'm curious about this. Let's do something with, again, we'll go to fixed point. And here what I'm going to do, make all these U8s. And the reason for that is I'm just going to assume a scale. So essentially 256 is going to be 1. So then every possible value 0 to 255 is going to like implicitly be divided by 256. So in this case, this would be like 8-bit multiplies. So to do that, this is 2 minus this, right? And so this is going to be 512 minus d as u16 as u8. It feels like it won't work for very large values. And I think this is actually crucial. Because I think the is it the numerator that needs to be double precision? And the quotient as well? I mean, I guess they all will be in this case. So I'm thinking if you take n by m to multiply, if you have an n-bit number times an m-bit number, you get n plus m-bit results. And I guess division would work similarly. If you divide an n plus m-bit number by an n-bit number, you should get an m-bit result, I think. Maybe I'm just spouting crap. It's always fun to not stream for a while and then come back and do something you don't know much about. Because, yeah, this needs to be scaled such that we can fit 2 at least, I think. Because like, let's take, like, the worst case. The worst case is denominator is 0. I'm going to ignore that one. So we're gonna assume the worst case is actually denominator is 1. 512 minus 1 is 511. And then we're multiplying all of this by 511, which obviously gets quite large. So that's pretty nasty. I'm gonna actually, we hit that case here, don't we? Okay, there's a trick here though, because if this is all fixed point, these actually we need to do our divided by 256 here. We need to like undo the scaling there. Does it work to just have 8-bit intermediates here? I don't know. Let's try. I think it does. First of all, long division, I think, is potentially slower. Well, okay. So first of all, long division takes a non-determinate amount of cycles. And I think they were saying, because then if we were doing it the long division way and we still want it to be pipeline like this, then we would still need the maximum number of steps. That'd be the amount of stages in the pipeline. I think they were saying that this one, as well as Newton-Raphson, approaches the result quadratically rather than linearly. So I think this does end up being a lot faster actually. So I think it is as pipelinable, but I think you need more stages typically. Whereas here we're giving up some potential accuracy, but it's gonna make the whole thing simpler. Or the whole thing is sort of faster and smaller in the end. Simpler is relative. But yeah. Yeah, so here this needs to be as U16. And this is U16. Maybe I'm going to do this as the shift right 8 just to keep it clear in my head. Does that work? 16. Right, because we need to cast these. I'm also ignoring signedness here. It's not just made to work with floats. It would work with either. Here we're going to multiply with overflow. Classic. I'm going to do this just to make sure we have enough precision here. Because I want to see it work. It's 20 divided by 5 is 30. No, I don't think it is. Yeah, multiplication is definitely faster. In fact, if you look at like Agner Fog, cycle counts. He's got these instruction tables. So if we look up like div or like idiv, are they not here? Maybe this is only for like SSE and the fun stuff. Yeah, he's got micro-op breakdowns here too. That's pretty sick. But I'm just going to pick a simple example here. So for example, this is latency, which is the number of cycles, I think. And you can see here, if we look at like mul, we're looking at like 3, 4, 5 cycles latency. Div is 24. So Duru 2 is correct that if it can be factored as a multiply, the compiler is going to do that for you. But if what you get is a multiply versus a divide, it's going to be slower. And this actually gets worse depending on the arguments. You'd use a divide if you can't factor it like a multiply. So a simple program might take an integer argument from a user. So if I wrote a program that said, give me a number between 1 and 10, well, I mean, then you could do a lookup table, but give me a number and I'll divide 20 by that number. I don't know what that number is going to be. So in order to support every possible case, I need to use a div. That'd be an example. And you could say, but why not take the reciprocal? But then you need to do 1 divided by their number to get the reciprocal. That's a divide again. And then you need to do a multiply anyway. So, and the other thing to consider is precision. With floating point, you might lose some precision in the reciprocal calculation. So even though in pure mathematics, n divided by m could also be described as n times 1 over m with parens, that's not necessarily true for floating point, especially with reduced precision. So sometimes you still need divide. Yeah, you could just have a lookup table as long as you I mean, you might need a 4 gig lookup table or whatever for 32-bit values. 4 gig by 4 for 4-byte results. And then you still need to do the multiply. That sucks. As far as I know, though, like really optimized hardware divisors will typically use a hybrid approach. So they'll usually use one of these like estimation things. But then for these multiplies, if they can reduce the amount of bits here, then they'll do lookup tables for those. I'm no expert there, so probably some clever stuff, but anyway. What did I mess up here? I'm gonna not convert these actually. In fact, let's do this. Let's just do everything just to make this easier. It's kind of dumb of me to do this on hard mode at first. Let's just do U32 here. We're still assuming like 8 bits here. We still shift right by 8. That's still 2. Yeah, so clearly this is growing. So I'm doing something wrong here. Now I think this is correct. This is 2 minus D. Yeah, I think this is all correct. And 2 definitely is this if we're looking at 8-bit numbers. And this kind of multiplication should be correct because this is scaled such that 256 is 1. So 2 minus this would give us that correct value. And then to multiply it, we need to multiply it and then also do that divide. Because essentially this is 2 by 256 minus D. And D is already scaled by 256. That's a key there. And so then we have N times 256 times F, which has the 256 in it. So we have 2 times 256s. And so that's why we need to get rid of one of those. And then N and D still have an implicit multiply by 256 here. I'm also going to do 2 shift left 8 here, just to make this a little clearer that that's where that comes from. And that these shift 8s align up. And so then, so what should happen is that this D should approach 256. That's what should be happening here. Is my input not in fixed point? It should be. I mean, these are definitely small decimals. Maybe it's the output that's not. No, I don't think that makes sense. And I updated the autocomplete stuff for VS Code, and this seems to be really buggy right now. But anyway. Yes, assuming these are, divided by 256. So this is still fixed point because there's that implicit divide there. So this isn't 20 and 5. This is 20 divided by 256 and 5 divided by 256. Maybe that's what you mean, that the input is not in fixed point format, because maybe you are actually right there. Because this doesn't represent 20 divided by 5 anymore. If this is 20 divided by 256, then this is going to be, let's see, 0.78 or whatever. And then this other one is 5 divided by 256. So I'm dividing this by this. Yeah, I guess that should still yield the same result, shouldn't it? Yeah, that should still get 4 because of the scaling, I guess. Oh, that's cool. Like Semtex. I should check that out. Yeah, this is still gonna be 4, but then we expect. I mean, the result will actually be. Well, the result will actually be 4. So then, wouldn't we expect if the result was actually 4, then we would expect that result to be scaled again. So we would expect, 4 times 256. So we expect 1024 to be the actual result, wouldn't we? I'm going to do 50 steps of this. And this tends to a number that's similar to that. So I actually think this might be working. No, I'm probably full of crap. That's really wrong. Maybe not. This is funny. I could, though, to try and make this simpler, I could try to pick some nicer numbers, which might help debug this. So let's take. I don't know. Yeah, 2/2. That's a good idea. Let's do that. 2/2. And then this should approach 256, which it seems to after, 500 iterations. Let's try that. Yeah. Okay. So this does seem to approach the correct result for that. In this case, this is 2/256. So this is, again, 0.00725 divided by 0.00725. Yeah, I should do that too. This is actually 2/2 because this is scaled. And then this should also... That didn't work. This should also produce the same value, but I think... I actually have no idea why that didn't work. To shift left 8 just to make sure that does the right thing. Yeah, of course that's correct. No, this should this should give us 256 here. So that should be. So let's do again 2 by 256. That's the scaling we have. So 2 shift left 8. Yeah, I should definitely do that. Let's go back to like 5 steps again. See what happens. Oops. Man, what is going on with my editor today? That's good enough, actually. F was 0. Yeah, and then if you multiply that, it doesn't work. Okay, so 2 is probably just out of range. In fact, actually, we know it is. Because D has to be in 0 to 1. So actually, we know that can't work. So this can only be like, yeah, exactly. Yeah, there you found it. You probably found it just before I did with the stream lag. Yeah, so you actually have to scale it such that the denominator is in this range. And that's less than 1 as well. So I guess if I did this, I mean, this probably works actually, but still. Whoops. Okay, so this, like 1 over 1 works. So I guess another thing I could do is, yeah. I guess what you would do if the divisor was large enough is you would just like shift until it's not, if it were too large. Because that'd be the same as multiplying both sides by 1/2, which is an equivalent fraction. So you should always be able to do that. So if I wanted to do 2 over 2, I could do like shift left 7, for example, which keeps it always in that range. What? Yeah, because 2 shift left 7 is 256. Which, let's do like 6 instead. I think that's more what I meant. Yeah. So, which is, yeah, equivalent to 128 over 128. And then it did actually take a few iterations, but it settled. With a little bit of precision loss there. So I'm going to go, let's do like 4 over 2. And we're going to reduce these just to make sure we have enough headroom. And you can see the result does approach 2. In fact, I want to stick some more iterations here. A lot of printing, but yeah, so what's happening here, and I think this was what was happening earlier, you can see that f is just over 1. And so that's why this numerator keeps growing, even though the denominator was stuck. So too many steps is detrimental to the accuracy, it seems. That happened here too. After like 5 steps, it got there. And then kept growing because of this 2 minus d yielding a value that was actually greater than 1. Because we want this to tend to 1. And after these shifts, it stayed there. But yeah. But okay. This works, right? So if I do like 16, right, it's now 16 bits. Is that what I wanted, actually? Let's do like 12. Something easy. Yeah, at least with those 8 bits, we didn't have enough precision to actually get it to yield 1. I think that might be different if we do more bits here. Hey, Pyro. I can see the same thing happens here. I'm a bit surprised about that, actually. But I mean, it does make sense. Like, you have this. Well, I would expect it to still get around there. I guess it does. I mean, it is correct here that 4095 should grow a little bit. problem is it doesn't. And then the numerator keeps growing as a result. No worries, Chief Sector. Sounds good. In fact, I'm going to be done here pretty quick too, I think. This is already as far as I wanted to get to today. Just again, to see this working, kind of get a feel for how accurate it is and what it takes. Because the other thing I need to do is actually plug in real values that I see in that rasterizer and see what happens. Because like this 64-bit division that I have here is not going to fly. So I need to figure out how many bits of precision I actually need in order to make this work. But I think this is actually correct. I think that just in fixed point, it's just not very accurate. Because again, like this looks like the right logic to me. Calculate an estimate for this multiplier, which ends up being near 1 because the divisor is near 1. And then when you multiply both, this one stays near 1, but doesn't quite get there due to the fact. Oh, by the way, this also is actually kind of important because this is always going to be a floor divide. So actually, we can probably fix this. I call it E for epsilon 6. So I'm going to do this. Now again, we may not have enough precision to improve the situation, but oh, there we go. It's still a bit off, but now because of the dividing, and now because of the more correct rounding, the denominator does actually tend to 1. I don't think I'm going to do rounding in the actual hardware implementation, but I don't know. It's nice to see that seems to work. And however, the value this is supposed to get to is 8192. So it is a bit off. But we have pretty limited precision. If I do like 14 here. Yeah, this is still a bit over, but gets pretty close. You know, I think also with, like, we want to do, like, let's do this. I think actually we need to fract bits. Do const. Whoops. I think we want something like this. Maybe. Yeah, and there it gets a lot closer. Because those values that we had, like 2 and 4 only shifted by a bit, were both pretty small compared to the amount of fractional bits we have. Yeah, and then this does a lot better in fewer steps as well. So the precision is definitely dependent on the values that we have here. You know, and I might be able to special case some of this too in hardware because I'm always, well, actually probably not. I know the value of the initial numerator, which is 1 in the hardware case or in my application, but since the numerator also grows, which is kind of the point of the whole thing, we can't just hard code that at every step. So we're going to end up doing stuff like 2 divided by 4. No. Two divided by 4 was 1/2, which at 12 bits is 4096. Or 2048. Yeah, that's correct. But I was thinking that like we're going to divide by smaller numbers. I mean, we already saw that actually. If I divide like 4 into 2, I guess 2 into 4 is the right way to say that. If I divide 4 by 2, we get a number that's greater than 1 here. So I think this is going to be, like, let's say A is always going to be 1. Yeah, it's all just scaling at this point, but I think it works. I don't really need to come up with better examples, I think. And then I don't know how many steps we're going to need again. That's going to need to be tweaked depending on the values we'll actually see. So that's why it's nice to actually have that rasterizer. Let me see, rust up show. Okay, that's 32-bit, which is what I want. So if I do build and test, let me cat that. Oops. Yeah, it's just going to run one of these. Let's just do that. Oops. I want to see the test rasterizer running again. I haven't seen that in a long time. And I think it'll just work if I do it like this. Because I need a 32-bit OpenGL, but since I have the right toolchain in use right now, or at least a 32-bit one, I think this will just work. It's really messy how I did this, how I hooked all this up to OpenGL, but again, it totally serves its purpose, so I'm really, really happy with it. Oh no. Oh, whoops. It's running and it's full screen. It changed my display settings. That's annoying. I didn't want it to do that. I thought I had a hook for that, actually. That probably fucked up the stream. You guys probably didn't see anything for a second. But I think that'll come back. We'll see. But yeah, I could have sworn that I had a hook in here for that. That's what this is supposed to do. I guess not. Let's see. It really doesn't matter which one of these I run, but it would be nice to get one that works. Yeah, so here I can run this in windowed. There it goes. Yeah, some of this stuff is so slow the way I have the renderer set up right now. Because I don't have it actually driving the rasterizer correctly, because it's a tiled renderer, and I think I have like the outer loops mixed up such that it actually loads the pixel data for the tile for every polygon, whereas normally what you do is you go through all the polygons and you scatter into polygon lists per tile. So you start with an empty list per tile, and for every polygon you populate all the lists for the individual tiles. And then your outer loop is you have a second loop after that, which goes, for every tile. And for every tile, you load in the current parts of the frame buffer that tile covers, and then you rasterize all the triangles into that, and then you move the data back into the frame buffer. Whereas now I think there's a lot of extra frame buffer moves, because for every polygon, instead of maintaining tile lists, for every polygon, I populate the tiles that it covers and then does that, which is, really, really slow. I think that's the sort of major optimizations next, and also like the render is not necessarily correct because there's a lot of features like I don't support, and there's actually more bugs here than I remember. I don't know why that is. Because I feel like this should actually work more than this, but maybe not. You can see like some of the features I have, like there is depth testing, there is texture filtering, at least bilinear filtering, there's blending. Also, the texture dimensions are fairly small. I think I only support 128 by 128, and I have to actually do some scaling in my OpenGL implementation to handle that. See you later, Drew, too. But yeah, it does still work. I just thought I remembered it being a bit better. I'm seeing more artifacts than I remember. Yeah, the console output, you're right, is totally not speeding things up. It's very helpful, though. But yeah, like a goal in the, I don't want to say relatively near future because I'm not working on this project all the time right now, but somewhat near future, I guess, is to have exactly the same output, but have it be produced by the actual FPGA, which means this is going to get even slower because it's going to have to transfer all that data to and from the FPGA. But there's no reason why it won't be possible. That's kind of the point. I'm going to run one more of these. Again, I do not remember that one being that ugly. But here we are. Yeah, exactly. It's gonna, well, it won't be OpenGL over serial because it's just gonna be like register writes to the rasterizer, the tiled rasterizer. So all the OpenGL parts are gonna be on the host still. But yeah, that certainly won't make it any faster. And I got to come up with some kind of generic way to do those kind of register writes and everything, such that I can support like any test that I want to do. The nice thing though is I don't know if I showed it earlier when I was like demoing that the thing actually works in the FPGA. Is that, well, I did show that when I like clicked reset, it would load a new program. But of course, the actual advantage of that is that I can change the program and then hit reset and it'll reload it, which is pretty cool. Yeah, and again, especially these textures are way lower res than they normally are in the actual demo. And the scaling that I do to get them this low res is not very good because I don't care. Because what I did is I initially supported like full res textures, but then in deciding on the exact feature set I want for the Xenowing, I had to start making those decisions. Like, basically, I want to have the whole texture resident in the rasterizer's local memory in order to do filtering, to be able to filter a whole texel per cycle. So I'm actually going to splat the texture memory into 4 different buffers. So it'll be like in little 2x2 squares. The top left is going to be in one of all the little 2x2 squares is going to be in one buffer. The top right is going to be another. Bottom left and bottom right. And that way you can pull a pixel from each of those buffers in one cycle and then do blending with all those the following cycle. And in order to have enough memory, right, or rather in order to keep the amount of memory that requires low, I'm imposing a 128 by 128 texture size limit, which again is a lot lower than this demo is trying to use, but I think will be totally sufficient for the Xenooing. So those are limitations that I kind of added after I started to get this to work. Also, this probably explains a lot of the issues. I don't think I'm actually doing depth testing right now, or at least it looks kind of messed up. So I think that's just a matter of this being like work in progress right now. Yeah, also doesn't use properly interpolated color. I don't think it ever did. Clip to viewport bounds within tile. It's another thing I didn't do. Yeah, so there's plenty of ways that bugs get in here, and I actually haven't looked at any of this code in a while either that actually drives the thing. Yeah, and you can see there's not proper culling either. Oh, I even create a new rasterizer for every primitive. That's funny. All this other stuff, so. Yeah, so like what's going to be really cool is that eventually once I have all this working, you know, even in just in Sim, then I will already have like essentially a driver for it in this test code, which then I need to port to C or figure out a way to use Rust on the console. I'm not entirely sure about that, but I'll probably port it all to C. And then I have a working rasterizer, and then I still need to do like vertex preparation. I need to come up with a way to do like transform and lighting on the system rather than soft floats, which is going to suck. I might end up doing soft floats for like calculating matrices, but then some matrix stuff, and then have some kind of pipeline vertex processor, something like that. But yeah, that's a long ways away. Anyway, I'm gonna go because it's getting really hot and I'm kind of done. So we explored some division stuff, which is what I wanted to do, and then I guess we'll continue on that next time. But yeah, thanks guys for hanging out. I'll get this uploaded ideally sooner. I put out all the latest videos on YouTube now so that I wouldn't like have to catch up again. So I'll try to be better about that. But yeah, thanks again guys, and I'll see you next time.